Oh, sorry. It's going to be probably way too loud. Sorry. Yeah, too loud. Too loud. Better, a little bit low. Yeah, a little bit lower. Okay, I think good now. Thank you. Okay, all right, good afternoon. Good, all right, let's start PyMol again. You had some experience yesterday. Today, let's start from the beginning again so that we can all be on the same page, something. And you have all played around with the primer. So let's start with the primer. So to open the primer, we'll just sort of try to follow that. Okay. So I'll skip over sections 1 and 2 because that's for your own enjoyment. And we'll go to section 3. Okay? So, and we need to open the file 7RFW. And I just double click it in my case. I don't know how you open it, but either way, just open PyMol, open that PDB file. So, there you go. So just like in Qt, I put the window to the left, I'll put it to the right. I'll leave some space over here so you can sort of see the primer that we have. So we'll sort of follow along with the primer, which you should be somewhat familiar with now. So this is what it looks like, right? Somewhat. So depending on which version of PyMol you're using, this is version 3. So only one text window on here. Version 2 will have 2 windows, one top at the bottom. But anyway, either way. And then you have this is the graph window, and this is the status, or many different things are shown here, object window, if you will. Okay? So, and PyMol is very different from Qt in the sense that PyMol is command line driven. So you have to start typing things today. And that's typed through this little prompt right here on your lower left. You have a PyMol prompt, you can type things right here. But to start typing here, you have to click on this window first so that you're in here. There is a prompt here as well. If you type in here, it's also recognized as a command, but you can't see what you typed. Unfortunate. So just keep on remembering you need to type a command, click on here, you can go in there. Okay? All right, so what do we say? So let's hide all the waters. That's what the tutorial said, hide waters, hide hydrogens. So let's do that. You look confused already over there. Everything's okay? Yes. Did you open this file? I'm sorry?
I didn't get which file.
So do you have the primer? The primer file right here? Open the Word file and then open the PyMol file, the PDB file. Okay? All right. So now you can move around a little bit. So let's say turn it upside down and then flip it around like this. You may notice at the very top here, the way I have it here, the compound is here, the top the structure is here. You sort of see as way at the top, this helix looks really weird. If you look at the helical ribbon, it looks very, very weird. See here? Let me you can middle click on to center it. Then you can sort of see that helix is going from a helix into an extended stretch here. So that doesn't make any sense, right? So we need to fix that. To fix that, that's a command that's in the tutorial called DSS. So that will ask PyMol to automatically assign secondary structure to your PDB file. So go back to your PyMol, go to the command, click on the command region, and then type DSS. Okay? Before you push return, keep your eyes here and see what happens when you push return. You see it's all gone now. It's makes a little bit more sense. Do you sort of see the same thing? Okay. So this is the way to fix the secondary structure definitions, because each PDB file has a definition of secondary structures, where the beta strands are, where the alpha helices are. Sometimes those definitions are correct. If you see a problem like that, DSS can help you fix the problem. Okay? All right. So what else do we want to do? All right, next thing we do is open this default.pml. This is a collection of setups that I like for my figures. So I'm giving them to you. You are free to modify to the way you like them, which is fine. I'll modify these occasionally myself, but that's sort of changing what it does is change the size of these ribbons and the thickness of the loops and then the thickness of the sticks and the stuff. It sets all those parameters. So just say, go to File, Open. And then you should see default.pml. Okay, and then just open it. You see, it made everything a little bit skinnier because I don't like the helices strand to be too wide. That seems to dominate the figures. I want them a little bit thinner. That's my personal preference. You can change the file any way you like. Okay? And then also I made the background white because when you want to make a figure for a paper or for your presentation, PowerPoint, white background is better than black background. But my students tell me that when I teach, white background they cannot see. So I will change mine here black. You can keep it white if you like, okay? So to change the black is very easy. Just go to Display, Background, Black. So I will keep mine black, but you can keep it white because you're looking at your screen. So whatever you like is fine. Okay, so we are all still together, mostly? Good, moving on. Okay, so let's middle click somewhere on this compound, anywhere you like, on the inhibitor, middle click there so you can center on it. Okay, middle click to center on it. And then zoom in a little bit using right drag, you can zoom in. Dragging your right mouse button, you can zoom in. So the reason I want to zoom in is you can see the colors. So red is oxygen, blue is nitrogen, in this case green is carbon, right? That's sort of the color scheme. But you will see the red that's in PyMol is not completely red. But anyway, I'll show you how to change colors of these things. Okay, so that's the commands here. So the command is color, red, name O star. That means all the atom with the O something will become red. And all the atom with the N something will become blue. And all the something that's C something, also residue 401, I'll show you why residue 401 will become cyan. So you can it's a very powerful command in PyMol to color things different ways. Okay, these are simple ways of doing it. So why residue 401? If you click on the inhibitor, it shows you residue 401 on the text window. Do you see that? Are we good? All right, so you see 401, right? So that's just typed in those three commands. When you type color red, make sure there's commas there, because without the comma, you get a mistake. Okay? So once you have that, click on somewhere else so that you don't get rid of the selection. So before you push return on the O, check the color here and see what the difference is. Okay? So let's try that. So go to the command window, color, red, comma, name, O star. Can you see okay? Well, probably there's no way you can see that in the back, but anyway, it's on the tutorial. Okay? And then you push return, see the color change. Do you see a change in your color? This one may not see. Okay? Repeat the command?
Yes.
So are you here?
Yes.
Okay, just type in this command in this window right here. That's what I typed. So color, red, comma, name, O star. That means the color, all the oxygen is red. Just like what's in the primer. Got it? So do the same thing for nitrogen. Color, blue, comma, name, N star. Unfortunately, PyMol is like this. It's not like Qt where you can do point and click, that's it. This is all command line driven. So do the same thing, color, blue, comma, name, and star. So you can see the blue become much bluer than the blue that's on the screen, right? Do you notice that? So that's 100% blue. The default color is not 100% blue. Okay? So are we okay? How about back there? You guys okay back there? Good? Okay. So now let's change the color of the compound. The last command. Color, cyan, name, C star, and Resi 401. There you go. You get something like that? So you color in all the carbons cyan, but only residue 401. Resi means residue number, but that's explained in section 1 of the primer. So residue 401 means that residue is colored based on your command. So only carbon atoms in that residue is colored. So you can now see a contrast between the protein and the compound. Does yours look something like this? Okay, going on. So let's zoom up a little bit. So you can see the entire protein centered sort of on the screen. The way I have it, like this. Inhibitor on top, in the front. And then, let me see what's going on. Oh, too far in the back. That's better. Okay. The compounds on top, going left and right, the protein is vertical. Something in this view. Okay? All right, so now we can color. So PyMol is very powerful in coloring ways, coloring things differently. You saw that yesterday. We can color as a rainbow. So go back to here, go to the object, go to C for color, and then spectrum, and then rainbow. Okay? So I'm leaving my mouse here so you can sort of see what I'm doing. Color, spectrum, rainbow. Got it? Okay. Okay, click on rainbow. You see something like this. Right? So just like what I mentioned yesterday, it's a ramp from blue from N terminus to red at the C terminus. In this case, the exact C terminus is the compound. You put in the same chain, but even though the C terminus is here, but small problem. Anyway, so it tells this helps you to say that essentially this protein has two domains. This domain up here, and another domain at the bottom. This domain is mostly C terminal because it's mostly red and orange, and a little bit of the N terminus here, and then you have another domain here, another domain up there. So it helps you to orient yourself where you are in the structure. So it could be helpful in that regard. Everybody? Okay. All right. So, you're happy with this color? Yes? I'm not. So I'm going to change it. Okay, so how do we change it? So again, go back to the color. You can see that many things, oh, this is so dark. I can't even see, so there are many options under here. So obviously, I'll show you what I'll show you. You are gonna play around with it, see what happens, okay? So we're gonna color by element, okay? So color by element, green for carbon. The second one is green for carbon, red for oxygen, and blue for nitrogen. And that's what we use. Okay, so color by element, and then green for carbon. Okay, so click on that. But back to where we were. So you can go back and forth very easily in PyMol in terms of coloring scheme and very different things. However, when we did this, we also colored the inhibitor green again. So we can go back. Are we all okay still? So we can go back, give the same command, but don't need to type it. So you can go to that window, push the up arrow, and the command is back. If it works for you, if it doesn't work, then it doesn't work. But for most, I think for most systems, it should work. It's like running. Are you familiar with Unix or Linux? This is just like Unix. Okay? Push the up button, the command comes back. You can push return, you get it. And if you don't, but let me show you another way of doing that. Okay? So you can click on the compound. So now you have selected the entire compound, right? You see they're selected. Now you can color only what you selected. And that's under this selecting. So under color of the select only, okay? And now you can color by element, make it cyan. There you go. You see what I did? So you select the compound, and then color only on the select one, and then color by element, choose cyan for carbon. Good? So this is the point, the click way of coloring rather than having to type. So that works too. So many ways of doing things, doing the same thing. Whatever way is easier for you, that's fine. Okay? So still good? All right, moving on. What's next? Okay, so here I'm being nitpicking here. So let me show you. So if you rotate around, in this view right here, you see a very small helix right here. Do you see that? Just above the inhibitor, you see a very, not even a full turn, probably 3/4 a turn. That's helical. If you spin it around, you can see that helix is very short. Okay, let me zoom in on the inhibitor. Zoom in. You see that. So essentially, actually, two consecutive ones. One here and one there in the same loop. Right, do you see that? So if you want, you can say that should be a loop. I can change it to a loop. If you don't care, then ignore me for the next 5 minutes. So it's your choice. So we can change that definition in PyMall as well. So as we did DSS, they'll ask PyMall to automatically assign secondary structures, but sometimes it still makes mistakes, so we can intervene and change that definition. So how do we do that? First, we need to find out which residue this corresponds to. So we find out the beginning and the end. So just click some residue before that little helix, somewhere around here. So what is the number here? That's 40. You might have clicked 39 or 38, that's fine, or 41. I don't know which way this one goes. And then we'll go to the other end. We're going to change both at the same time. Click to the other end. That's 51. I'll click 51. You may have clicked something different. This is fine. Okay? So now we know the range from here to here, 40 to 51-ish. Okay? All right, so now we can define this range as a loop rather than a helix. Understand what I'm saying? So that's the command that's next on the tutorial. So order 40 to 52 / comma. Unfortunately, that's the way things are done. And then SS means secondary structure equals L means loop. Okay, so type that in. Unfortunately, you have to type it in. Or you can copy and paste. Since you have it open, you can copy and paste. That's what you're doing. Oh. Very good. Very good. Okay, yes. So she reminded me, you can copy and paste. You have this window open, copy and paste. Thank you. I will type. So order, that means you're changing. Oh, see, I typed in the graphics window. Alter 40-52 SS equals L. Oops. Oh. Okay. So it should tell you, it should respond, tell you modified how many atoms. You should see that on your text display. It told you something's right. I did typing something wrong, it gave me an error because I forgot the quote. Either double quote or single quote. I forgot that, so it gave me an error. Well, so I changed it, put in the quote, and then it's fine. Okay? So that's sort of the way to give that command, but then they only changed the definition, but then you have to re-display the structure. So that's the rebuild command. You rebuild it. So now you type in rebuild, and then see what happened to these two little helices. Do you have the primer? Do you have the primer? Yes, it's in the primer. Right here. Right here in the primer. Okay, so type in rebuild, and then return. So now you can see those helices are gone. Now they are loops now. Okay? Repeat which one? Okay. Did you do this? You did this already? Then type in this. Type in rebuild, and then return, and they will change. Okay? I'm sorry. Huh?
The previous one I'm not able to know. It's showing error.
The previous one? About? Let me see. I'm not sure I understand. Oh, right. You copy that. Okay, and then return. Oh, I'm sorry. It probably should be a single quote. Try single quote. Yeah, right now it's a double quote. Try the single quote. So single quote, L, single quote. Yeah. Oh, okay. All right. My apologies. So if it didn't work, Using double quote, use single quote. So in the tutorial or in the primer, I have a double quote, which did not work, right? So in single quote, that should work. Let me change the primer right now. So then, I'm sorry. Like that. If you do it this way, then it should work. Okay, let me save it. See, it's good to come all the way to India to teach. Now I know I have a mistake in my primer. Beautiful, thank you. Okay, so now you're all here? Okay, so if you couldn't get this to work, this is a minor thing, so don't worry too much about it. And then, okay, so now the next part, we'll, in the primer, we'll look at the interactions near the inhibitor. Okay? And this, well, let's see what happens. Okay? So we're going to center on the inhibitor, click on, let's say, on this proline-like residue, center on the C alpha, so we'll center on the inhibitor. Now you drag to zoom in. So you can sort of see everything on the inhibitor. And then, so now you're seeing everything. So now we're going to slab. So rotate your middle wheel. You see things disappearing. Just twiddle your middle wheel. You can see the thing disappearing. Not too much, but you don't want to see too much either. You want to see mostly things around the inhibitor. So essentially you're slabbing in, displaying a thinner slice of the structure. That's what it's doing now. So you have it. Okay? So now we have the protein shown as a ribbon drawing or cartoon drawing, inhibitor shown in a stick, but we don't know what protein residues are around the inhibitor. And the way I do it, I show everything. I show all those residues in the protein as lines. So that's the next thing we're going to do. So click on Show S on the protein part, on the complex, and then lines. So you show everything as lines. So now you see everything that's around the inhibitor. Do you see that? I know it's very complicated. Bear with me for a second. Do you see the same thing? Okay. And so now to find out which one interacts worse, you just jiggle your view a little bit. You can sort of see where the inhibitor is sitting and what residue is close to it. I mean, obviously, if you leave the thing still like this, it's a 2D image. Doesn't help you that much. So you always use your mouse to move the structure around a little bit to give you the third dimension. Move it back and forth a little bit. Okay? So, and then if you look here, at the very end of the inhibitor, there's a cysteine residue from the protein. You see that? There's a cysteine right here, near the very end. Do you see it? You see that? You see that cysteine? At the right-hand side in this view, there's a sulfur yellow structure. This is the side chain of cysteine. Okay? The only thing we want to do here is select the cysteine. So click on the cysteine, anywhere on the cysteine side chain. So you have selected it. So identify this cysteine as close to the inhibitor. Good? Yes? Yes. Okay, now we're going to show this residue as sticks also. So how do we do that? We'll go to the selection, show as sticks. Okay, so go to select, show sticks. There you go. So now there are sticks. Okay? And then after that, we're going to hide all the lines because the only reason we did all of this, I want you to find where the cysteine is. Now we found the cysteine, we're going to hide all the lines from the structure. So then to do that, you go to hide, H, hide lines. Oops, beauty of Pymol 3. Oh, again. Okay. So you should have something like this. All the lines are gone. You show only protein now as a cartoon drawing, inhibitor as a stick drawing, and the cysteine shown as a stick drawing. Everybody has similar thing? Thank you. Good. So you asked the question yesterday, right? I still remember. There you go. So what do you see when you look, ask that question? What do you see? What do you notice when we do this? So here you have a protein, which is green. Here you have the inhibitor, which is cyan. What happened here? So some chemistry happened, right? So you have a covalent bond between the inhibitor and the cysteine. Is that right? So I guess we will not go much beyond this on the structure. I'll just mention that here. So Professor Shukla mentioned this morning proteases. So this is SARS-CoV protease. And the compound you see here, I forgot the name of it, but that's a drug on the market for SARS-CoV. Okay? And the SARS-CoV protease is a cysteine protease. What does that mean? That means use cysteine as a nucleophile to attack the carbonyl carbon or the peptide bond to break the chain. So what happened here is essentially this is the active site cysteine. So this is the catalytic cysteine of this SARS-CoV protease, and that has attacked this carbon of the inhibitor and forming a covalent bond. There is no way to draw a structure here. So anyway, so in the compound, this is a cyano group, carbon triple bond N. Do you know what cyano group? Nitrile, cyano. So carbon triple bond N. So when the cysteine attacks, the triple bond becomes a double bond. And that's how you form a covalent linkage. So basically, this compound is a covalent inhibitor of the SARS protease. That's what I want to show you. Did you get it? Okay? All right. You guys okay? All right. So I do this all the time. So I turn on the lines. I can see everything I want to see. But when you turn on line, you're probably swamped by so much information, right? Too much. Okay, good. So there's another way of doing it, which I did not put in the primer last night or this morning. That required a little bit more typing, unfortunately, but it's probably easier for you to see. Basically, what this command does is show everything within 6 angstroms of this compound. So it's more focused. All 5 angstrom is up to you. So what we do is, for this, I did not put it in, so unfortunately you have to type it in. So we use the select command in Pymol, and then you can use any name here. It's just a name for your selection. So I call the inhibitor side, and then comma, and then commands by res, means you select the whole residue in this protein, which we loaded, within 5 angstrom of residue 401. You know what that is, right? That means that's the compound. So that means this command will give you everything within 5 angstroms of that compound, and then put that into this object. Okay? So can you type it in? Can you see this okay in the back? Or let me see whether I can zoom it in. Okay. So type in this line. I'll give you time. Got it? No?
After the fourth.
Yeah, I don't have this in the primer. Yeah, so this is new. This little paragraph is new. So that's why you cannot copy and paste. I'm sorry. I put it in this morning. So my apologies. That's why you got to type it in. I don't know how to share that with you. So I'll share it on the screen. Yeah, please, copy what you see on the screen. Okay? So I will do the same. So select inhibitor site, comma, BIRES 7 RFW within 5 of Resi 41. Oh. You should see something like this. Did you see something like that? Oh, yeah. Good idea. Take a picture. Okay, so this little piece here is, sorry. This is a powerful command as well. So once you type it in, it should tell you on the text window selected how many residues. It also show you all these little red squares that show the atoms that have been selected. It also opens an object here with the name that you gave it. You should see that on your right-hand panel as well. Got it? Okay, so now you have selected them. You have not shown them yet, so we need to show them first. So you can either say show lines as a command, like this, or you can just, rather than typing, you go here, say show lines. It's probably faster, so let's just do that, see what happens. Show lines. And then you click somewhere else, so now you see everything within 5 angstroms of the compound. So now you can jiggle around. It's easier to see because it's a much more focused display. You're not swamped by things far away. Oh, this command here, this top one. Okay, all right.
After this one, tag to this one, show lines in
You can do that, or you can go here, show lines. Because once you type that in, you should have an object open for you here. Do you see it? Okay, go there, say show lines. You should get the same as what I see. I mean, this command you can modify to your satisfaction with whatever way you want to do, but this is just beginning. So also mention, if you want to do something in PyMol, you don't know how to do it, Google. Okay, Google it, you'll find the answer. Are we all okay? All right, so I'll go back to the graphics window. You can see all the side chains, all the residues that are near the compound. Okay? Okay? I'm sorry? You see it? What's there? I can't see there. Invalid selection names 7RFW. Oh, you loaded different file. That's why.
And sir, for cysteine, how do you do the cysteine cysteine part?
The same thing. So you have to say 7RFW, no SS. You loaded a different file. That's why.
No, how we can remove this? This is not showing in your.
I'll show you after this. I'll show you again. You when you rotate around, you find the cysteine again. You see it. Okay, yeah. Change that to a 7RFW, no SS. You loaded a different file. Okay. All right. You got it. Okay. All right, so this is another way to find neighbors or bonding site for your compound. And again, the same thing. When you rotate, you can look at the right of the compound, you see this covalent bond to cysteine. So then you can highlight it, show as sticks, same thing, okay? But this might be easier, more4 you can make it 4 angstroms, 6 angstroms, whatever you want to do. Okay, so finally we're done with this. We'll turn it off. To turn it off, you just go to the thing, say hide lines. And that's gone. Okay, go to the inhibitor, that object, say hide lines. And that's gone. Right? The inhibitor site object. Yeah, go to that object, say hide lines. Because we're hiding lines here, so then it's all gone. Okay? All right. All right? So one more thing. You click on the inhibitor. So you have selected it. So that's under select. And then under there, you say show as spheres. So now you see atoms as spheres. Do you see something like this? Okay. And if you think the sphere is too small, we can change that. Okay. Let me show you another very powerful interface in PyMol. Are we all okay? Are we all here? All right. So let's make the sphere bigger, let's say. How do you do that? So there's the settings command, menu, setting. So click on setting at the very top, the menu bar, right here. Say edit all. Under settings, say edit all. And then it opens a little window which contains all the settings in PyMol you can modify. So you can see the scroll bar way up here. There are many, many, many parameters you can modify. So have fun with that. Today, for now, let's just change the radius. And that's called, so you type in the search bar here, say sphere. And then it gives you all the commands that contain the word sphere. And then you down here, you see sphere scale. See that on yours? Something called sphere underscore scale. That tells the size of the sphere. Right now it's 0.4. So make it 1. Okay? Let's see what happens. So just click on it. And then make it 1 and return. It's bigger now. Did it work for you? Yes? That's yes. Okay. However, what you see here now, we showed hydrogens too. Little white spheres are hydrogens. If you don't like them, you can go back there and hide them. So you can go back to select, hide hydrogens, and then they will disappear. So let's try that. hydrogens all, they're all gone. Okay? Do you see the same thing? All right. So that's another way to, sometimes I show you this way to give additional emphasis on the compound, because that's the focus of your study. That's the most important part of your study. You want to really highlight it. So you want to show them as spheres, occupy, really draw your attention to it. To help the readers, help the reviewers to say, okay, that's the most important part of the structure. So that's why we do this. Okay? I mean, this might be the overkill to use a 1 as the scale, but you can play around with it. So 0.4 might be too small, 1 might be too big, so 0.7, halfway. Play around to whatever you like. Okay, so now we're done with that, so we're going to hide that too. So go back to select, and then hide spheres, and they're gone again. Okay? So these are simple little exercises in PyMol to get you in the door, so you can sort of know how to start playing with your structure. Still good? Okay, moving on. So you can close this window when you're done. Just close it, or you can leave it open. Either way is fine. Okay, so now let's zoom out again, and then slap out so you can see the entire protein, sort of in this view. Okay, something like this, roughly. So now the next thing we'll show is the protein surface, which we showed briefly yesterday. So for that, just go into show, surface. And then very quickly, the surface shows up. Colored, carbon green, oxygen red, nitrogen blue for the protein. And then of course, the compound, so it only creates a surface for the protein or nucleic acids. The compound doesn't know how to make a surface, or doesn't make a surface, so that leaves, you can see a very nice little pocket for it. Right? So you can see the pocket. Zoom in. Very nice pocket for the compound. So essentially, because this is the protease, the compound mimics the substrate of the protease. So this is how the protease recognizes the substrate, by using these binding sites. Pockets on the surface of the enzyme. And then the cysteine is hiding behind here. That's why we don't see it, but then by rotating around, you'll see it right here. See right here, the yellow is the sulfur. The compound goes into the yellow because that's the covalent bond. Right? So all of this information is there if you know what to look for. They're all there. But then you say, I don't like this figure because it's too busy. Right? Because you have red, blue, and green. It's way too busy. Sure, I agree. We can change the color. So for that, we'll go back, color, green, and green. That means we'll color everything green. Originally we color by element, now we color everything green. So you can color by any color you want. So let's stay with green. So color green. So now everything's green again. But then the compound's green too, which we don't like. So we'll click on the compound, and then go to select, color by element, and make it cyan, which you should know how to do now, right? So now you have a nice contrast. You're not distracted by all of these other colors here. So you have green, the protein, cyan is my compound. Good? So again, when you make figures, think about don't make the figure too busy. So the main point should shine through so that you can look at it and say, okay, that's what I want to see. The reason I want to show this, essentially, you have a nice pocket for the binding of the compound. So this part goes very deep, and that's a side pocket here for this group here. Okay? We're still good? All right. So now let's hide it. We're done. Oh, let's hide the surface. So now we're back to the cartoon drawing and the compound. So you probably saw what I did, because in PyMol 3, if you have PyMol 3, these little things have a little gap in between them. If you click on the gap between them, it's just the same thing as click on over here. If you click over here, see what happens. You hide the display. See, it's all gone. So if you click in between these little icons here, it's the same thing. It makes it disappear. Anyway. So that's sort of one way of hiding the display or something. You just click on that display, this bar right here somewhere, and then the whole thing gets hidden. Okay, so that's that. What else do we want to do? Okay. Electrostatic potential, red, white, and blue colors. Let's do that. Just show you how it's done. Okay, so that's under A, action. So under action of the protein object, and then say generate, and then vacuum electrostatics, and then protein contact potential. So it's a 3 sub-menus. So go into action, generate, vacuum electrostatics, and then protein contact potential. Do you see that? Got it? If you got it, just click on it. You got it already. Yes? Got it? All right, I'll click on mine. And it made that. So you should see something like this, right? Okay, so it generated the electrostatic potential. Blue means positive charge, red means negative charge, yellow, white means neutral. This is the color bar right here. Okay, but it also hid the original structure. It only shows the surface now. So we can show the structure again. So click on that bar to show the structure, and then you can zoom in back on the compound. So you can sort of see the bonding site is mostly neutral here. There's some negative charge here, some positive charge further away, but generally. So this is probably a more colorful figure. So sometimes we show that as well, the electrostatics, especially shows information that you have a very nice positive charge region that binds nucleic acids, for example. So that gives you a sense of where that is. So this is something that you can use as well for making figures for your paper or for your thesis or for whatever you want to do.
How to make a video and put on
How to make a how to make a figure out of this?
video.
Video of this, if you don't rotate, there's no video. It's a 2D stationary structure. I'll show you how to make movies. So I'll show you how to do that. Yeah, that's the last part. We only got an hour in. We have plenty of time. We'll be here for another 2 hours, 3 hours. Okay, so this is okay? Yes. All right, so now let's hide them. Just by click on the bar, then they disappear. So we're back to here again. Thank you. All right, so last thing we're gonna do is look at, there's in PyMol3, there's a little thing called sec, sequence. In PyMol2, I think it's just the letter S, but either way, click on it. And just like in CUT, you see the entire sequence of your protein up there. Are we still good? Shaking head or nodding head? Okay, so same thing. This is a live sequence. You middle click on it, you center on that residue. You left click on it, you select that residue. So play around, see what happens. Middle click anywhere you like, see what happens. Okay, you're not doing it, I'll do it. You can see everything shifts. But you only center it, it doesn't show what it is. And then to really show what it is, you left click, now you select that residue. It gives you the selection marker. Okay, so this is the way for you to find out what, if you know where you're going, which residue you want to go to, this is for you to quickly go there. Show the sequence, you can scroll down, there's a scroll bar here, back and forth, to where you need to go, middle click the center there, and then show the side chains, whatever you want to show. Okay, so if you scroll down, you see there's the inhibitor right here, and then waters at the end. But okay. All right. Okay, so when you're happy with what you've done, then click on that again to hide the sequence. We don't need the rest. Okay, so now let's center on the compound, zoom out a little bit. Let's say you want to make a good figure for your structure. You want to select good view, right? So let's say you twist around, find a good view. In my mind, this is a good view. The protein is vertical, the compound horizontal. So that seems to be a good view for me. And then you can save this view. You can also change the depth queuing. So now if you twiddle the wheel, you can see you start cutting things away. And then the other way, everything starts showing. And this is not good because everything's same brightness. That's not good. So you want something called depth queuing. Things the front is brighter, things in the back is a little bit wider. So you sort of see, okay, this is in the front, this is in the back. So you move your middle wheel until you start cutting into your structure. Like this, essentially. So I'll just start cutting in, you back up a little bit. That's probably a good view for what you need to do. Okay, so this is something you can play around. So once you're happy with the view you have, you can save it. And that's this command here. View V1, or whatever name you want. I call it V1, V2, V3. View 1, View 2, View 3. You can choose whatever name you want, and then store. That way you can store it. Okay, so let's do that. So now it tells you view stored at V1. Okay? The reason we do this is now you can go around, make all kind of weird things to your structure if you want, change your orientation, whatever you want to do. And you say, okay, I want to go back to where I was. Then just type view V1, then you're back. So to do that, just type view V1. No argument, it goes back to where you were. Got it? So this is I do this all the time when I make figures, because the view is good, but then you may want to change which one you want to show as sticks, which one you want to show as sphere, all of these other things you may want to change. So you keep the view, you can go back, add and subtract things. But you don't select the view again. Okay? But be careful here. We save the view, but the view is saved in this session only. One critical thing in PyML, which I never mentioned in COOT, you always have to save your progress. In PyML, you can save the session. Very powerful command. So to do that, you say right here, File, Save Session As. Okay? So go to File, upper left. Save Session As. It comes up with a dialog. You can tell it what name you want, whatever name you like. So since we're working with 7RFW, 7RFW. Oh, I have a file called that name already, so I'll replace it. So now you saved it. So next time I'll open that file, that view 1's in there as well. If you don't save it, it's lost. Okay, so keep that in mind. Well, it'll happen once or twice, then you'll remember. Okay? Still good? All right, let's see what's next. Oh, yeah, I see that. So now you have a display like this. How do you make a nice figure out of it? High-res figure for publication, because in the paper you need 300 dpi figures, right? 300 dots per inch figure, very high resolution. How do you do that? If you do a screenshot, not good enough. But it's good for your phones and stuff to send to your friends, send to your parents. But if you want to send it to a paper, you need something fancier than that. So for that, you do something called a ray tracing. That's this command, ray 1000, comma 1000. That means 1000 pixel by 1000 pixel. That's the image it'll generate. So do that. So now it made that file. It shows essentially the thing sits in here. If your scale is too big, something may be cut out. You scale down a little bit, and then render again, do ray tracing again. So leave it like this, don't touch it. If you touch it, you lost it. You have to do it again. So this is the image you can save, which is 1,000 by 1,000 pixels. Do you see that? So now you save as a PNG file. So just give the command PNG, and then the file name. So
Quality of the figures are PNG and TIFF file.
which one?
TIFF files are better than PNG file.
I'm sorry?
Quality of the figure.
Uh-huh.
Save in PNG or TIFF file.
PNG. Only PNG. I think it's only PNG. Well, is it TIFF? I don't know if TIFF is possible. I will always be using PNG. So I guess somebody can Google, can you save the image as TIFF files? But I have always been using PNG files.
Because the resolution of the figure are more better in TIFF file.
Uh-huh. Yeah, it's more layers and stuff. Yeah, but you can. This has no layers, labels on it at all. So what you do here is you make this figure, now you put in labels on it, all that stuff, right? So that you can do in any program you like. So I use Photoshop. You may use Illustrator or other. I don't know. That might be special program in India for doing labeling graphics program or PowerPoint. You can do that in PowerPoint too, right? So anyway, so give the command PNG. And now this is called 7rfw.png. So now you saved it as a PNG file. Okay? Yeah. I'm sorry. Yeah. You have it upside down, but that's okay. Yeah, there you go. Yeah, turn to the left. More. There you go. So that's close to what I have. Right? And then it's just too big. You scroll out a little bit. Yeah, there you go. And then save the view. View v1 store. Remember that's the command on the screen. View v1 comma store. Let's save the view. You good? Too easy for you. You guys okay back there? All right. Okay, you saved it. And now you can ray 1,000, 1,000. Yeah. Okay, you're using the interface. That's fine. So that's too big. You need to scroll. You need to zoom out a little bit. It's because you cut out the top and the bottom. So you zoom out a little bit so you can see the entire molecule. Okay. So if you go to that folder, there should be 7rfw.png somewhere, I hope. Oh no, they're in here. So, and that's the PNG file that you can crop, label, whatever we want to do. And then if you find the figure is too small, the resolution is too small, okay, sometimes it does happen, then you can go back and render it at 1,500 by 1,500 or 2,000 by 2,000. It's up to you. Depends on what you need. You don't want to be too big because it takes forever to render. But in the end, you want the figure to be about 300 dpi, something like that. Okay? All right. So click somewhere else, then that window disappears. Okay. All right. So next thing was looking at secondary hydrogen bonding interactions between the compound and the protein. Okay, that's in your primer as well. So for this, with middle click on the compound again, zoom in. We should have saved the view that we found earlier, but anyway. Okay, and then we found all the residue nearby. That's this thing we showed right there. So let's go back there and say show as lines. So they all come back again. Right? But then you see a problem now because we colored everything green earlier. So the arginine is all green now. So you want that to have some kind of nitrogen, oxygen colors. So you want to change the color of the nitrogen and the oxygen, but you don't want to change the color of the carbon. So you can do that. So go there, go to that inhibitor site, color by element, select the first one. The first one is changing colors of the nitrogen, oxygen, and the sulfur. Doesn't touch the carbon. Leave the carbon where it was. Okay? So if you do that, you can see now you have everything colored correctly. So that helps you to tell which residue it is. Okay? So now let's zoom in some more. So something like that. Now with the compound going up, okay? So this is CON. So this is the N terminus, that's the C terminus. We'll make it going straight up in this view. Do you have it? Okay. And then we need to show the protein as well. Protein now is shown only as a main chain. No, only as the side chain. We don't see anything in the cartoon itself. So we have to temporarily hide the cartoons. Okay, so more exercise. So go to the protein, say hide cartoon, which is right here. Because that's what that is. So hide the cartoon. Now it shows the protein backbone as well. You have the same thing? Similar?
So can you please start?
Okay? So by doing so, we're showing essentially the compound as a stick drawing, the protein as a line drawing, but we can sort of see the interaction between the compound and the protein. For example, in this view here, if I jiggle a little bit, you can see this carbonyl oxygen is hydrogen bonded to this nitrogen of the protein. Do you see that? Do you agree? Okay. So we can draw a hydrogen bond between them. So how do you do that? Under wizard, up there, way up at the top, wizard. Measurements, second one down, measurements. Okay, that's in the write-up as well. And then you should come up with something like this. Please click on the first atom, and the little menu shows up here. You should see something like that. And then just click on the two atoms, the oxygen, the nitrogen. Okay? So do that. And you show a dashed line between them. Got it? Okay? You're nodding now. That's good. You're following me. That's good. Okay? Everybody see something similar? So now the challenge is let's find the next one. Okay? So let's look around, see whether we can find another one. What about this amide in front of the carbonyl? This amide, what do you think? That's hydrogen bonded to this carbonyl oxygen, right? So we can click on these two, draw another bond because that's still active. So let's click those two. And then you have made another 100 bond. It tells you 100 bond. It also tells the distance, 2.6 and 2.9, I believe. Okay? So this is all the way to see interactions between the compound and the protein through main chain 100 bonding interactions. Essentially, the compound's forming an anti-parallel beta sheet with the enzyme because the compound goes up because CN. That means this is an N terminus, this is C terminus. So compound goes this way, protein goes this way. So it's an anti-parallel beta sheet. Okay, that's typically how proteases recognize substrate by forming a beta sheet structure with a substrate. Okay, so I think we'll do two. That's enough. I think the tutorial you can do more, but let's just do two today. So once you're happy what you did, say done. So then that little menu goes away. Okay, that closes the measurement. Okay, so now you can see when you do this, new operators start showing up. Measure 01, measure 02. These are the two things. You can turn them off by just clicking on them. It disappears. Okay, got it? Are you guys okay? Good. All right. So now, do you like the color? Yes. Oh, okay. I don't. So, I typically, when I show the hydrogen bond, I show them in red. Okay. So how do you make it red? You should know by now. Go to color, make it red. So let's do that. Color, red. You had all kinds of different reds. I just go to the top red. Now you have a red dashed line. Do the same for the second one. Color, red, red. Okay? And then the last thing you may want to try is get rid of this label, because that can be annoying because it's very small font. That's the distraction. So you can remove it. To remove it, you go, well, you need to hide it. So hide, labels. It's gone. Hide, labels. So now you have just the dashed line to indicate the hydrogen bonds. Good? Okay. All right, so we're done with this part. I think that's this piece right here. We're done with that. So let's see what's next. Yeah, so we did that already. So all of these we're done. And then we're going to hide these two very easily. And then we'll show cartoon again. So let's go back, show it cartoons. And then we hide the lines. Okay, so now we're back to where we were. And we hide the two measurements. Okay, so now we are all over the place. Let's just type view V1. You're back to where you select the view. Right? That's the beauty of saving views. You can easily go back without having to worry about it. Okay. That's all good? Okay, so now we have done one structure. The next part is to compare with a different inhibitor complex. So we read into the second structure and compare them. Okay? So to do that, we first have to open the PDB file. So file, open, and there's something called 7RFR in your folder. Oh, wrong one. Oh, I did not put it in. I only have this one. Okay, so open that one, 7RFR, no SS. Do you have that? Okay, open that file, please. Okay. So now it's open, and it's in a different orientation. So we have to overlay them first before we can compare them. So how do you overlay them? Well, action. So go to action of 7RFR, and then say align. Right here, align to molecule to 7RFW. Got it? Okay. Take 7RFR. Do you have that file open? You don't have the file? Okay, sorry. Then watch me. Okay, just watch me then. Don't be distracted. Watch me. So you read the file in, and then you can align them by using action align to a molecule 7RFW. Okay, you can download 7RFR from PDB as well if you want. So this is all the PDB files. So you align, they lined up like this. Okay, so they're overlaid together. And then it creates a little object called a line something. You can just hide it, doesn't matter. So now you zoom into the compound. So you see essentially
Again, how to align? How to align? Can you explain again?
how do you
Align.
also under action, A, align, and then to molecule. And then under there should be 7RFW. And then click on that, you align them together. Okay? So now we have two structures, one cyan, one green. So now we have a little bit problem color contrast now. And then the inhibitor, both are cyan. So let's change color a little bit. So we click on this inhibitor, and I just select. We make it color by element, make it salmon colored. Is that better? So you can sort of see the difference between two compounds, right? Very, very different. Especially this compound, which is part of 7RFR, is much bigger here. If I zoom, turn around a little bit, you see it's much bigger substitutes. And then because of that, if I center in that region, zoom out a little bit, you can see conformational changes in the protein. So this loop moved back a little bit because this has a bigger group here. So you need to move back a little bit to make room for the compound. So that's sort of the idea of comparing different structures, give you insight how the small molecule interact with protein and how plastic the protein can be to change conformation to accommodate the compound. So that's something you will be doing as well. If you have two structures, you need to overlay them, compare them. This is one way of doing that. Okay? So if you want to practice this 7RFR, just write it down when you get back, download that from PDB, try it out. Okay? The file came from the PDB. It's not mine. It's from Pfizer. 7RFR. So the one we looked at earlier is 7RFW. This is 7RFR. It's written here as well. It's in the tutorial, 7RFR. Okay? All right. So, okay, so we're going to hide this now because I showed you how it works, so you can play around with it. The last bit, okay, well, actually not the last bit. The last bit is this. So as you can see, PyMol, I showed you only the very, very tip of the iceberg. There are many, many commands. You can see so many menu bars up here which barely went into. So many options here as you click on each. There's so many different options as well. And also the command line. So it's a very powerful program. This only gets you in the door so they can play around with it. But to learn more, look at the manual, Google some. If you want to do something and don't know how to do it, Google PyMol, and then what you want to do. Chances are, AI will tell you how to do it. So that's the beauty these days. You don't really need to have anything written down. You just Google it, and then you come back with it. Okay, so let's try them out. Okay, so everything okay? All right, now the last bit, not the last bit, the next bit is, I guess you're curious how to make a movie. Yay. Good, I'm glad to hear that. So how many have done making a movie in PyMol? Have you ever done that? No? All right, let's make a movie. So to make a movie, how do you make a movie? You have many, many scenes, right? So 60 frames per second, 24 frames per second, whatever it is. So PyMol is the same thing. You define a few scenes for it, and then you to interpolate between the scenes to fill in the blanks for you. So you just define the major stop points, and then you converse between them, make a movie out of it. So the most important point here is select the scenes that you want to show, and PyMol will do the connections for you. Okay? So I'm using PyMol 3. So if you're using PyMol 2, making movies a little bit different. So, but the beginning part saving scene is the same. So the first scene we'll show is the overall structure, right? And that we saved already as V1. So let's go there. view V1. Oh, I'm typing in the wrong window again. There you go. So let's say we start from here. Well, I'll start from here. You can start anywhere you like, but my movie will start here. Overall structure, the best view of the compound. Okay? So you like this, and then there should be at the very top a command called scene. Right? Near the menu bar, scenes, next to setting. Okay? Say, click on scenes, save new scene. So now another menu bar should show up on the right, on the left. The first scene you saved is called 001, scene 1. So now you can imagine what happens next. You put in scene 2, scene 3, scene 4, scene 1000 if you have the courage. Okay? So what I like to do, you saw in my talks, I like to rock the molecule a little bit to give you a third dimension. So let's say we start from here, turn it by 90 degrees around the vertical axis, to give you that rotation. So how do you do that? You give the command, but you don't want to use the mouse because the mouse is not accurate. You want to do an exact 90-degree rotation. To do that, you say turn y, comma, 90. Or sorry, maybe it should be minus 90, as in the tutorial. Okay? So let me change that to minus 90. That just tells you which way you turn, to the left or to the right. Okay? So you do a rotation. So now, when you turn 90 degrees, compound is on the side, because in the first view, compound in the front, turn 90 degrees, is on the side. Right? Are we here? All right. So if you like it, click on the plus sign. And if you're in PyMol 2, you don't have that. How many don't have this thing here? You all have this? Speak up, please, if you don't have it. You all have it? Okay, good. So then, as I just did, you click on it, let's save this scene as 002, second scene. Okay? Now let's say we'll rotate back. So you can do that by just saying view V1. I'm making a very simple movie, just to give you a sense how to do it. So now we'll go back to here, we'll save it again. Say plus, save it again. Okay? Now we're going to zoom into the compound to see how that interacts. So click on the compound, zoom in, select a good view, zoom out a little bit, so you can sort of see the compound mostly, not much protein to distract you, something like that, maybe. Well, you can find up something better, something like this. And then we can save this view as well to be safe. So first you do is say view V2 store. So now you saved second view. So now next time you go to the compound, just say view V2, it goes there. View V2 comma store, just like you saved how you save view 1. Right? So you like this scene here, so let's just say, okay, we'll save it. Yeah. Oh, I thought you have a question. No. Okay, so now we'll do a little bit of rocking around the compound. So let's say we turn back 30 degrees, forward 60, back 30 to go back to where we were. Make sense? Okay, so same thing. So turn Y minus 30, save the scene, turn Y 60, save the scene, and then you can go back to where you were by doing view V2, save the scene. So we have it, right? So, and then you can also, in this case, show the surface as well if you want. Or you can say, okay, I'm okay now. Let's just go back to the beginning. So the movie is a full circle. Okay, to do that, view V1, and then save the scene again. So now we have a movie with 8 scenes. Right? Got it? So now we have to program that into a movie because you have 8 scenes, but the separation, the time between the scenes, you can control. How long the movie is, you can control as well. Okay? So go to movie, and menu bar, movie, new composition, the very top one. So now you have a movie timeline here, which contains 5 seconds, which you can change by using this edit command, but for now, we'll leave it 5 seconds, okay? So now we can individually add the scenes to the movie. And this is sort of how I learned how to do it. That might be a better way, but so go back to the top, click on the first scene to select it. Got it? The scene 001. And then near the bottom, there is a add to timeline. A little button, click on that. Okay? So now you see the scene always add to 000 because that's where the green bar is. That's where you add the scene. Or you can make, I guess we can try it. Let's see what happens. So right now this scene is either times 0. The green bar, I believe, is where you add the scene. So let's move it down a little bit, see what happens. So then we move the green bar down a little bit. Right here, let's say. And then we click on scene 002. And then we say add to timeline. Yep, it does do that. Okay, so now you made 2 scenes. Okay, so now you pull the bar down a little bit more, place this third scene, we'll move it down a little bit more. So scene 3, right here, add the timeline. And then pull it down a little bit more. Scene 4, add to timeline. Put it down a little bit more. Scene 5, add to timeline. Oops, didn't work. Okay. And then scene 6, add to timeline. And then there's a scroll bar at the bottom here. You can scroll to the right to finish the 5 seconds. And then scene 6, move the green bar down. Scene 6. Add the timeline. Scene 7. And then the last one, scene 8. Add to timeline. So there you have it. So you had a movie of 5 seconds with different scenes spaced around it. You got it? No? So what's missing? Do you have the scenes? Did you save the scenes? No? You did save the scenes. Okay, so this is the part you don't quite follow. Okay, let's go back to the top. So you go select the first scene. So your timeline's empty right now, is that right? There's nothing in there. Okay, go scroll back up, click on 001, and then click on add to timeline here. Do you see a little square show up near 0? Half the scene show up near 0. Do you see that? Yes? And then there should be a green bar at the top. Just drag the bar down a little bit, and then you put in scene 2, scene 3, scene 4, scene 5. Okay, everybody got it? Yeah?
In my movie, Legends movie is not so a new combination.
Yeah, this is the old. Yeah, You're not using which version of you're using the new version of Pymol, so then you're using the old version of making the movie. So stop that, and then go back to movie.
Movie.
New. Oh, you only have the legacy movie maker.
Yes, yes.
You don't have the new movie maker. I see. So okay, that's fine. Program,
Program.
scene loop,
Okay.
and then let me see. That's fine. And then 1 second pause. Oh, no pause.
No pause.
Yeah.
And then
You should have another movie. All right, so let me see. Program and scene loop. Oh, you did stay loop, scene loop, steady,
steady.
and then 1 second each.
1 second each.
Right.
And then
The movie should show up. I don't know what happened to it. Oh, there you go. You have it. Now you play Clay. Yeah, there you go. Because you're using the old version of Pymol. That's why. Okay, so everybody has this scene set up? Yeah, okay. So now, whether you're happy or not, you click on play. And hopefully it plays. Let's see what happened to mine. Why is it not playing? Okay. There you go. So you had the movie, spin, zoom in, rock a little bit, and then zoom out. You saw it already. Okay, so you see the same thing? Okay, so you made your first movie. Congratulations. So, we have half an hour. What do we do now? Anyway, so now you made your movie. Very poor quality, but beginner's luck may be pretty good as well. But anyway, this gives you a flavor of what can be done. You can be really careful, make a very fancy movie. And what I haven't shown you is, obviously, that's the distance between this scene and that scene. That's a time distance. So you can adjust that by just dragging this back and forth, adjust how fast it transitions between different scenes. So you have a lot of control over the process. Okay? So it's a very powerful interface for you making movies. So you're the director now. You can choose whatever you want to show in your movie. And this is a very powerful medium to really convey the third dimension of your structure, because looking at something like this, it's boring, it's 2D, it's dead. But when you have a movie, it gives you the third dimension. Okay, so one last thing, a minor detail, you need to save the movie. Otherwise, it doesn't work. Okay? So I'm not going to adjust this, okay? I told you how to do that, so in the interest of time. So to save the movie, go to File, Export Movie. Got it? And then I usually make it 450 by 450 so that the movie is not too big. So that's the size of the window, 450 pixels by 450 pixels. And the rest doesn't really matter too much. And draw fast, MPEG-1 encoding, and then you click on Save Movie As. Okay? Click on that. Got it? So, yeah, 450, 450. That's what I showed up there as well, anyway. To make the movie smaller, because otherwise you make a humongous movie, you put it into your PowerPoint file will be 200 megabytes. Can't do anything with it. Okay? So save movie as, and then you give a file name, so 7RFW. So now you start rendering the movie, going through everything, one frame at a time. And then it creates a little file on your desktop, right here. Where did it go? Oh, it's done already. Okay, too late. All right, it's done. So that should be in your folder, 7rfw.mpeg. Do you have it? Okay, bring it up. Show your first product. Okay, double click. And this is my movie. Okay, let me impress you. Let me show. So, did you get something similar? Yes? Yes? Okay? Well, at least gives you a flavor of what you can do. And then the rest, of course, is up to you to practice, make it good. Make your movie good, and then you can also make the movie longer if you want. This is a 5-second movie. You can make it longer if you want. If you save 20 scenes, you don't want a 5-second movie because now you're way too fast. People have a headache looking at your movie. So you have to sort of, this is too fast already. I'll probably slow it down a little bit, but this is only for teaching, so yeah. Okay. All right, let me start the movie. Yeah. Okay, so everyone okay with making movies? All right, so we have a few more minutes. Let's look at some other things. Yes? No? Maybe? Okay, let's move on. Okay? All right, so let's close the Pymol session. We're done with this now. We didn't save the session. If you want to save it, please save it, because view 2 we defined is not saved. So next time you get back in, you will see only view 1. You don't see view 2. So you save it now, next time you get back in, you have both saved. Okay? All right, let's close this. So next thing we're going to do is look at AlphaFold models. I'm sure you'll be spending a lot of time looking at the AlphaFold models, right? So this sort of help you look at how to look at those models. So in your folder, hopefully there is a AlphaFold or CIF file in your folder. Do you see it? AlphaFold.cif, C-I-F. Do you see that? It's alphabetical, so below 7 is the AlphaFold CIF. You see it? Do you have it? Okay. CIF is the next generation of PDB. You all know about PDB, right? Protein Data Bank, PDB. But PDB is being replaced by CIF. CIF means crystallographic information format. Just so another format for structures rather than PDB format, it's a CIF format. But Pymol opened it just as well, so double click on the CIF file, it opens up. Okay, so let's open it. There you go, you have it. So here you have a protein shown right here. And first thing you do, you color by chain, how many proteins there are in here. Okay, so you can color by chain, so go to color. Oops, I clicked it. By chain. So now you can see there are two proteins here, right? One in green, one in cyan. Two separate proteins. That's why they're colored differently. And then you have these gigantic loops on the surface. For example, this one right here, and this one right here. Very large loops floating around on the surface. Okay, so I shouldn't say that. So are you familiar with AlphaFold?
Yes.
So you know the confidence in AlphaFold? No? Yes? I forgot. No. Confusing me now. Okay, if you don't know, so AlphaFold make a prediction. For each residue, actually each atom, it gives a score, which is the confidence on the prediction. And the score is above 90, is good. I'm not on the network anymore, so the Wi-Fi doesn't work for me anymore. Anyway, if you go to any AlphaFold model, well, you'll see that dark blue is highly confident. Light blue is confident between 50 and 70, I think. No, sorry, 70 to 90. And then between 50 to 70 is so, not very confident. Below 50 is basically garbage. So that's shown as orange. So orange is really bad, yellow might be, and then cyan and blue. So that's how it's colored. And this confidence is encoded in the temperature factor. Remember temperature factor from Monday? In the PDB file or in your structure file. So you can color it in PyMol by coloring the temperature factor field. Okay, how do you color temperature factors? So go to color, spectrum, and then you see B factors. B factors same as temperature factors. You click on that, and then you color it for you. Got it? Okay. So, and that's what you see, right? Something like that. Okay? So I just told you, red is very bad in AlphaFold, but here everything's red. Does that mean it's really bad? It is. Huh? Very low confidence. Is that what you're saying?
Yes.
It's a trick question. Because, remember, PyMol thinks temperature factors are real temperature factors. So real temperature factors go from low to high. High is bad, low is good. So, but then confidence numbers are the other way around. High is good, low is bad. So when you color this way, red means very high temperature factor, which means very high confidence. So I'm used to looking at it this way now, so I don't bother to load it the PyMol way, the AlphaFold way. So red means good, green actually is bad, blue is bad. Okay? So these loops that I showed you earlier, they are blue. That means they're bad. So, but then if you publish something like this, the people will be confused because everybody used to looking at PyMol figures, AlphaFold figures like orange, yellow, cyan, and blue. So I have given you in the folder another file called AlphaFold.pml. So that's a script that colored the structure using using AlphaFold color scheme. So open that file. So file open and click on that file, and you'll see the difference. Okay, so go back, file, open, and then AlphaFold.pml. Okay, got it? So now you see this is the AlphaFold color scheme that you're used to, right? So now you have blue, cyan, yellow, and orange. So orange being the really bad ones. Got it?
Yes.
So I gave you that file, so you can copy it, take it home with you. So when you look at AlphaFold models, you can use that file in PyMol yourself and make it color it based on PyMol, based on AlphaFold. Okay? All right. And then last thing about this, you can see these loops on the surface of orange, which means they have very low confidence. So for something like this, not too bad. But something larger, you can be distracted by these long loops that are really very low confidence. So maybe you want to hide them, right? You can hide them based on their confidence. So that's basically right here. Oh, no, right there. So you can give the command, hide everything, be less than 50. That way all the low confidence region disappears. So give it a try, see what happens. Okay? Wrong window again. Okay? Now when you do that, all the orange colors are gone, right? You only left yellow, cyan, and blue. So the ones you have some confidence in. Even the yellow, probably not great, but you don't want to be too strict in your cutting. I chose 50. You can choose 60 if you want. So this is up to you. 50 is where the low confidence cutoff is. That's what I used. So now you look at mostly the high confidence region of your prediction, which hopefully is correct. Doesn't mean it's correct, because there are other factors, other criteria to look at for AlphaFold. So, which I don't have time to show you. Yeah. I'm sorry. This you can open in COOT as well. COOT can open this file, color by B factor, same way. Same way. You can look at it in COOT as well. Yes, that's right. It's just like a PDB file. COOT can open zip files as well. Okay. We're okay? So this gives you a flavor of how to look at the AlphaFold models, which I think will be very powerful, because you will not be, most of you will not be determining your own structures, but you'll be looking at AlphaFold predictions. So this gives you a sense where you are. Okay, now done with that. Last thing. So I mentioned conserve in my lecture. So essentially that's coloring based on sequence conservation, right? It's a server in Israel. You just Google conserve, you find the server, or you see my slides. And then you go there, upload your PDB file. It gives you another PDB file that has a temperature factor field encoded with conservation. Just like in AlphaFold, they encode confidence in the temperature factor field. In conserve, conservation is encoded into the temperature factor field. Now you color based on conservation. And then you also give you a little Python script that come with the PDB file that you can color it. Okay, so you should have a file called conserve.pdb in your folder. You have that? Okay, open that. Okay, so here's the structure. Doesn't really matter too much what the structure is, but anyway, this is what the way it looks like. And then there is the little script that came from when you run conserve. It gives you this little Python script, conserve new Python. So that's the file you open next. So just go to File, Open, and then select that Python script. Okay? And then say Open. Got it? Okay. So now you can see it changed coloring. Right? Did you see that in yours? So, okay. And this doesn't look that impressive yet because it's a ribbon drawing or cartoon drawing. So now show it as a surface. Okay, show your protein as a surface. So go to Show, Surface. Okay, now the viewer move around until you find something like this. Do you see something like this? Yes? Okay, so what does it tell you? It tells you, first of all, it's a surface, very deep pocket here, right? And also very conserved. So the conserved convention is purple is conserved, blue is not conserved, white is in the middle. So this is highly conserved deep pocket on the surface of this protein. And we know this protein is an enzyme. So where do you think the active site is? So obviously, the active site should be right here, where it's highly conserved. So this can be very helpful for you to show that that's the important part of the molecule. That's why it's so conserved among homologs. So you see that kind of figure. Actually, I have the figure even up. This is from our structures. I made that figure and put it into the paper. So it's in the paper. Something like, not the exact same view, but showing that conserved pocket for the active site. Very informative as well. It shows you how conserved everything is. Okay? So another tool they can use. It doesn't take too long. Conserve takes probably 10, 20 minutes to run, something like that. You upload your PDB file, then you download the new PDB, the Python script, then you have your figure. Okay. All right. What else should we do? Repeat this? Okay. So that's right here. So you have this. That's the very end of the primer. So you open the PDB file from Conserve. So that's Conserve the PDB. And then you open the Python script by using file open, and then select this file. You open it. You color it that way. And then you show it as a surface. So you go to Show Surface, and then you have. And then you select the view you want. Got it? Yeah. Okay. Huh? Let me see.
Sir, you said about how to do morphing between two
Oh, morphing. Okay. Thank you. I was going to show that tomorrow afternoon, but since you asked for it, let's morph. Okay. All right. So we're okay with this now, right?
How to download a consult server? Consult server file, and how to make
How do you?
a consult server file?
Oh, you upload your PDB file to a server, to Conserve server. You Google Conserve, and then you find this.
Server are
Any PDB file.
web server. Different web server. Consult server are different web server.
No, you have your PDB, you have your structure as a PDB file. You upload to the Conserve. You download that, and then upload that PDB file to Conserve, and then you create the PDB file for you. Yeah. Okay. So we will next learn how to morph between two structures. And for that, actually, you don't have 7RFR, right? So how do we morph between two structures? You don't have two structures. Okay, watch me for now, and then we'll do it again tomorrow. If you can't download 7RFR, you can download that, but either way. So, okay, so let's go back, start 7RFW. Oh, sorry, wrong way. I saved the PyMol session, so 7RFW.pse, that's what I saved. I'll go back there, but I didn't save the inhibitor, but whatever. So now let's open 7RFR. And then align. So this you have seen already, okay? View V1. So now you have two structures. You can morph between them. Okay? So how do you do that? That's under plugin at the very top. Plugin. And then at the bottom, morphing. Okay? Select morphing. Then you can morph from one structure to the other structure. So let's say we morph from 7RFW to 7RFR. And then we choose how many states. Let's try 60. 30 is a little bit too fast. Let's try 60. Okay, you have to make 60 states in the morphing process. And then we choose linear interpolation method. Rigimo, I guess, works, but it takes forever for me, so I'm staying away from it for now. So use linear. Okay. So now it will morph between the two structures in 60 steps, making a movie. Okay, so just click on morph. And you can see the spinning wheel is doing calculations. It'll take a couple minutes to do. Oh, it's done already. So you see the morphing going on. So now we can zoom into the inhibitor. And then you can sort of see how the morphing is happening. And then we can hide one of the structure, the starting structure. Oh. Anyway. Oh, I have to stop it. Okay. So now you see the conformal change as a movie, right? So we did a very simple morphing. You only show the main chain as a cartoon. You can also include side chains and everything else. They will also be morphed. The small molecule will not be morphed because it doesn't know what to do with them. So they require the protein to be the same. If it's not the same, you cannot really morph them. You can see the structure changing from the green structure to the cyan structure. So that's how you morph it. And then in the end, you can export a movie as well. And then that will give you a movie. You can change the view anything you like in this way. Select any view you really like, and then save the movie. And then that will be your morphing movie. The one I showed you is basically made this way. So I made going this way and then coming back. So that's why you see things going back and forth. So I made two movies and then put them together. And then you see one movie going open and close, open and close. Otherwise, it only open, it doesn't close. It's a little bit jerky at the end because you open and then go back to close right away. So you open slowly, close slowly, open slowly. You make two movies. Morphing from A to B and then B to A. Make two separate movies, put them together, and then you have this back and forth motion. So we can try that again tomorrow afternoon, making a morph for something else that you do have, so you can play around with it. Okay? So that's sort of the idea. So everything is under plug-in and morph. And then you just saw the interface actually is quite simple. And if you want to make movie a little bit slower, you can make 100 frames, for example. Then it'll be a little bit slower. So that you play around, see what you're happy with. Okay, any questions about these? I mean, we're done with PyMol. We're done with the time too, actually. So, any questions about PyMol or Qt? So you're all good? Yes, learn something useful? Yes, sir. Okay, good. I'm happy to hear that. So, all right, with that, we're done today. So keep on practicing. Yes, so see you all tomorrow morning. All right.